Theoretical recap. An IP address, Internet Protocol address, is a unique numerical identifier assigned to every device connected to a network. IPv4 addresses are written in dotted decimal notation. For example, 192.168.1.1, composed of 4 octets ranging from 0 to 255. Every network has two reserved addresses. The network address, for example, 192.168.1.0, and the broadcast address, for example, 192.168.1.255. Devices such as routers, switches, computers, printers, smartphones, and servers each receive one or more IP addresses depending on their role. A router typically holds at least two IPs, one on the LAN side and one on the WAN side, acting as a gateway between networks. A subnet mask, for example, 255.255.255.0 or /24 in CIDR notation, defines which portion of an IP address identifies the network and which identifies the host. The default gateway is the IP address of the router interface your device uses to reach external networks. Dynamic IP assignment is handled by DHCP servers, while static IPs are manually configured. Critical infrastructure devices like servers and routers usually get static IPs. Common mistakes beginners make: confusing the gateway IP with the device IP, mixing up private ranges, 10.0.0.0 out of 8, 172.16.0.0 out of 12, 192.168.0.0 out of 16, with public IPs, and forgetting that a single physical device can hold multiple IPs, for example, a router with LAN and WAN interfaces. Mini example. In a home network 192.168.1.0 out of 24, your router might be 192.168.1.1, your laptop 192.168.1.10, and your phone 192.168.1.15. Workshop brief. This workshop builds directly on the concepts you explored in IP address and packet concepts and observe an ICMP packet with ping. Your goal is to move from theoretical understanding to practical identification. You will map real or simulated network equipment to their respective IP addresses, justify your associations, and document your reasoning in a structured report. This is a foundational skill in cybersecurity. Before you can pen test, audit, or secure a network, you must be able to identify what is on it and understand the addressing scheme in use. You have 48 hours to complete and submit this workshop. Work alone or with help, but the analysis and the written justifications must be your own. You are encouraged to consult your previous course materials, official documentation, RFC 791 for IPv4, IANA private address ranges, and any relevant Internet resources, Cisco documentation, Network Chuck, Professor Messer, etc. Step 1. Set up your environment. Choose one of the following two scenarios depending on your available equipment. Scenario A. Use your real home or office network. Scenario B. Use a network simulation tool such as Cisco Packet Tracer, Free, or GNS3. If you choose Scenario B, build a small topology with at least one router, one switch, 3 end devices, PCs or servers, and one printer or IoT device. Assign IP addresses manually to each piece of equipment using a private address range of your choice. Document every design decision you make. Step 2. Discover and list all devices. Using the tools available to you, such as your router's admin interface, the command line tools ipconfig, Windows, or IP address, ifconfig, Linux/Mac OS, ARP-A, ping, and nmap for example, nmap SN 192.168.1.0 out of 24 for a host discovery scan. Enumerate every active device on your network or simulation. For each device found, record its IP address, its MAC address if available, its host name if resolvable, and what type of equipment you believe it to be: router, PC, printer, switch, phone, etc. Do not stop at simply listing results. Think critically: why does a device have the IP it has? Was it assigned by DHCP or statically configured? How do you know? Step 3. Associate addresses with equipment roles. For each device you discovered, write a clear association table with the following columns: IP address, subnet mask, CIDR, device type, role in the network, assignment method, DHCP/static, evidence or reasoning. Pay particular attention to the router. Identify its LAN IP, your default gateway, verify it with traceroute or traceroute, and if possible identify its WAN-facing IP as well. Identify which device acts as the DHCP server. If two devices share the same subnet, Explain what that implies for communication between them. Step 4. Analyze and document your findings. Write a structured report, minimum 400 words, plain text or markdown, that includes a network diagram, hand-drawn, drawn with draw.io, or generated by packet tracer is acceptable. Your association table from Step 3, a section explaining the subnet logic you observed or designed, a section identifying any anomalies or unexpected devices, and a short reflection, 100 to 150 words, on why accurate IP to device mapping matters in a cybersecurity or DevSecOps context. Think about reconnaissance, asset inventory, and attack surface reduction. Do not simply list facts, demonstrate that you understand what you observed. If something surprised you or did not behave as expected, describe it and propose an explanation. Advice to overcome difficulties. If Nmap returns no results, verify that your firewall is not blocking ICMP or that you are scanning the correct subnet. If you cannot access your router admin interface, check the default gateway with ipconfig or iproot and try opening it in a browser. If you are working with packet tracer and IPs are not communicating, verify that the subnet mask is consistent across all devices on the same segment. If you are unsure whether an IP is static or DHCP assigned, check the device's network settings directly. Always verify your assumptions with a second tool or method. This is good security practice.